Okay, so I'm going to try to wrap everything up in one more video. Hopefully we can do it. There are a few other quick things I wanted to make sure we talk about that come up in chapter 15. So something that we've been talking about since the beginning, since we talked through chapter 14, and even before that in other lectures, we focused on outliers, on the importance of understanding if you have outliers in your data set and how they're going to affect certain measures that you can compute. Things like means and standard deviations and, of course, correlation and your slope and intercept. So all of those things are affected by having outliers in the data set. And it's important to note that correlation and regression are not resistant to outliers. You might remember this idea of resistance. That means that there are certain measures that don't really take outliers into account when you're computing them. They're more resistant to outliers. Correlation and regression are not, because you need means and standard deviations to figure these things out. And we know that means and standard deviations are impacted by outliers. So I wanted to kind of just try to illustrate this with an example to again get you thinking about why outliers would have a certain impact, and also to get you thinking about the fact that not all outliers have the same type of effect on what we're doing. Okay, so here's one particular example. So in this example, notice along the x-axis we have study. So study here is the amount of hours that a student spends studying. On the y-axis we have quiz. That's a quiz score. So all the dots in this scatter plot are students, and for each student we figured out how many hours they spent studying for the quiz and what their quiz score was. So notice here that I don't have the line in here, the regression line, but if we had it, it would be somewhere in here. And you're probably noticing there's this one unusual point here. So what's going on here? So lots of things could be leading to this. So this is a student who didn't really study very much, but got the highest grade. So, it could be that student is just very smart, doesn't need to study very much, just really knows things, picks things up rather quickly. Maybe this is a student who's repeating the course, knows the assignments, again, doesn't need to study as much because of that. Maybe it's a student who cheated. We really don't know. We don't know why we're seeing this unusual value, but it's there. And so what we want you to think about is how having that value in the data set is going to affect your correlation and how it's going to affect the regression equation. So this particular value is pretty far from the regression line. And so remember that as we have more scatter around the line, we have a weaker relationship. So the less scatter we have around the regression line, the closer things fall to the regression line, the stronger the relationship. So having this particular value here within the data set is actually leading to a weaker correlation. If we removed that value, the correlation would get stronger. And doing some detective work might lead us to think, we need to remove that value. This student is not really representative, or this student shouldn't really be part of the sample, or maybe we made an error in terms of entering information. So we'd have to think about how to best handle that outlier, but we need to know it's there. We need to talk about it. We need to think about how it's affecting the analysis. Now let's think about a slightly different situation. So again, we have the same things that we're looking at. So X is study, amount of hours studied. Y is a quiz score. This time we see something a little bit different. So again, the regression line's not in here, but if it was, it would look kind of like this. This time we have an unusual point. This is a student who studied the most, did the best, so has the highest quiz score, studies the most. This person is not far at all from the regression line, but is far from the rest of the values in the data set. This particular individual is extreme along the x-axis, meaning that this individual has, the highest value of X compared to everyone else. In this case, this person's also pretty extreme along the y-axis. With this particular example, since this point is not very far from the line, having this point in the data set is actually strengthening the relationship, because this point, it's almost like it's anchoring the regression line and it's pulling all the other points close to the line. If you suddenly removed that point, let's say we figure out later that student is not typical, maybe we have a reason for removing that student, we have good justification for that. If we were to remove that value, a lot of things would end up changing here. So notice that we're removing this value, and so suddenly we'd have a different range of X values. We'd have a different range of Y values. So the standard deviations of X and Y are going to change because that value is not here. The averages are going to change. The whole regression line would change. It would shift and move around. The regression line over here might not really shift as much, but over on this side in the second plot, it would. And so removing this value would actually lead the correlation to become weaker. So over here, removing this would lead to a stronger relationship. Over here, because of where this outlier is, removing it would be weaker. So we want you to think about this and just think about the fact that not all outliers are created equally. Not all of them have the same impact. Sometimes removing an outlier could strengthen a relationship. Sometimes it could weaken the relationship, depending on why it's an outlier, depending on where it's falling within the scatter plot. So always, again, that's why you want to first create your scatter plot, look for any unusual values, and then think about how they're going to impact the analysis. Another extremely important idea and we talked about this in chapter 14, is that correlation does not imply causation. So we just want you to always be thinking about the fact that if two variables are associated with each other, if they are correlated with each other, that does not mean one variable causes the other. To really know if one variable causes another, we would need to conduct an experiment where we can control for possible lurking variables, as many as we can think about, to really make a good argument for causation. And this is actually something I found at one point on Facebook, I think. I thought it was a really nice example of why we don't want to jump to the conclusion that because two things are related to each other, one must cause the other. So I'm hoping this is something you can kind of look at later and think about and remember as you're working through this content. But why is it? Why is it that we cannot jump to the conclusion about causation? So if you want to learn a little bit more about this, there's a video that you might want to look at. It's there's a link here. It's up on YouTube, and it's very short. It's not even 2 minutes long, but it's all about how at one point in time in United States history, there was some thought that maybe eating ice cream caused polio, and that's because doctors and researchers were noticing that the incidence of polio seemed to be spiking during summertime. And that's when people are eating a lot of ice cream to try to stay cool. So there was a thought that maybe these variables had a causal relationship. So why is it, again, that we cannot jump to the conclusion of causation simply because a couple of variables are associated with each other? So I wanted to attempt to illustrate this with some diagrams here. So again, we might be really interested in trying to figure out, does X cause Y? Okay, so only a well-designed experiment is going to help us in terms of making a good argument that X causes Y. But even then, it can still be difficult to show causation because, even if you've really done a good job of setting up an experiment, it's always possible that there are some lurking variables that you just haven't thought about that could be coming into play and could be leading to any type of association you're seeing between your variables. So one thing that chapter 15 talks about is it tries to make a distinction between confounding and something called common response. And I wanted to stress right away that both of these things, what they have in common is they're both trying to show you how a possible lurking variable or a third variable could be coming into play and affecting the relationship that you're seeing between your X and Y variable. But how that lurking variable is having an impact is a little bit different. So I'm hoping as you're seeing this word confounding, you're thinking back to chapters 5 and 6 when we were talking about experiments, because that was a time when we introduced this idea of confounding. We talked about how a certain lurking variable could get mixed up with your explanatory variable or your independent variable, and both of them are affecting the response, and you can't really tease apart which one is having an impact on the response. So that's confounding. So in this case, we wanted you to think about an example of, let's say we're looking at how much daily exercise someone is getting, that's X, and we're looking at hormone levels, Y, so levels of a particular hormone. We think that exercising is going to affect these levels of this hormone. But there might be something that we're not really able to control for, and that's how much sleep a person gets. So that's Z. So both X and Z have this relationship on hormone levels. But because we haven't controlled for Z, we really don't know when we see these hormone levels, is it because of X, or is it because of Z, or is it maybe because of some combination of the two? Because we were unable to control for Z, we just really don't know. So we can say that X and Y are associated with each other, but we wouldn't want to say that X causes Y, because obviously there are some other things going on. So this is a case of confounding. Both of these things, as you see, are related to Y, and so it's hard to tease apart the effects of each one. So how does this compare with what's called common response? So again, we have the same scenario here. We're looking at daily exercise, which is X. We're looking at hormone levels, which is Y. We think that they're related to each other, or we see that they're related to each other. Well, there's this third thing, this lurking variable called sleep, the amount of sleep that you're getting, Z in this case. So the amount of sleep is related to how much you can exercise. Obviously, you can't be exercising if you're sleeping. The amount of sleep you're getting is related to your hormone levels, or your levels of a particular hormone. Because Z is related to both of these, because X and Y both have Z in common with each other, it seems like X and Y have a relationship with each other, but it's quite possible that they really are not related at all. They only are showing to have some kind of relationship because they're both related to this third thing, sleep, that we haven't controlled for. So this is what common response is. There's a third lurking variable that's related to both of our variables, both X and Y, and that makes them seem like they're related to each other when in fact they really might not be. So that again is a reason why we wouldn't want to jump to the conclusion that X is causing Y, because there could be something they both have in common that is leading to this relationship. Okay, so I'm going to pause here. Just for you to kind of think a little bit more about this. And again, we're going to have one more quick video. We just have a few more things to wrap up, but I'll give some more examples of these things so that you can see another instance and think about how common response is different from confounding. Okay, so one more video. I'll be right back.